and when we pull this out, for each connection between two general states, let's call it R4. Now remember these labels here. They are, now this is a GNFA, right? These labels here now are regular expressions. Right? They're not limited to only symbols in your alphabet, symbols in your input stream. They're more complex than that. Now this is a generalized NFA. So the labels now are regular expressions. Okay? Right, so for this general state, whatever it is, Qi, let's say it'll have a connection to QRIP, the one you're going to pull out, rip out. Okay? And QRIP will connect to some general state, QJ, and call the regular expression on that connection, that arrow, call that R3, and there'll be a loop back to itself, and let the regular expression on that arrow be R2. Okay, so it's quite general. All right, now we're going to rip out this one, so that means these three arrows disappear. They get ripped out with it, because they're connected with QRIP. So this state disappears and these three arrows. Now you can repair the damage that does in the following way. Well, have a look at this state. Now, before you rip this one out, you've got these two arrows coming in, right? R4 and R3. But so if we do the following, like we rip this out, these three are gone, and then we replace this label here between these two general states, Qi and Qj. If we replace that by this, effectively Qj is it's acting in the same way. Well, this whole thing, right? These two states and this regular expression here is acting as though it were this. Now, can you see why that's the case? Like, what is this regular expression? What's going on here? Well, you've got R1 and then concatenation with R2 star. Now you can loop around here as many times as you like, right? So that's the equivalent of starring this regular expression, R2 star, and then again concatenation with R3. So effectively, what this is, the regular expression that results from these three is R1 concatenated R2 star concatenated R3, and there it is. Okay, and then you union that. Now remember, now why union? Because when you have, so when this one disappears and you want the effect to be the same as this one, you union this one with this one. That was one of the conditions, also one of the three conditions from earlier board. Okay, so you union that with the regular expression that comes out of this, which is this here, and union with R4. Now what is well, the whole thing? What's it meaning? Well, it's a GNFA. Okay, so if you're in this state and your input stream matches this regular expression, it's compatible with this regular expression, then you transition to the next state, which is this one. Okay, so this with this now modified label, this this thing, this I don't know what to call it actually. This from this transition, if you like, from this state to that state, behaves in just the same way as this. Okay. Now this is the old machine. That's the previous phase, if you like. That's your GNFA before you ripped out this state, and this is like the new ripped machine. This would be your GNFA with one state less. Okay. Now, doing this is quite general because these are two general states, and now of course the rip state will connect to others. So you'll have something like this between other connections. For different values of I and j. Right? You'll need to do this for all of them, because remember this state will connect to all of them. There'll be an R3 connect. Well, maybe not R3, but there'll be a connection arrow to all the other states. Remember, that was one of the three conditions from the previous lecture. Okay, so it's quite general. So you for any pair I and j, you can repair the damage after you've pulled out this state by doing this. Okay, that's sort of the essence. Now this is still all part of the proof idea, right? It's still rather hand wavy, a little bit vague. It's not the formal proof yet, but we're getting close. Okay. So this and this effectively, they function in the same way. You will transition from this state to this one if your the input signal or the substring, if you like, matches this regular expression, and that state transition will behave in the same way as this. I hope that's clear, because this comes from this, and that's quite general. Okay. Yeah, whatever these are. All right. Okay, now we can actually start the proof, the formal proof. But before we do that, we need to do a little bit more theory, notation, I guess. Now, the formal definition of a GNFA, which we haven't done yet, that's what we're about to do, everything's much the same as just an NFA, with one essential difference, and that's the transition function, the delta. Now here's the formal definition of the transition function for the NGFA. Sorry, the GNFA. It's like printer's soup. Okay. Now you may remember for the DFA, the find error automata we've done so far. The transition function would the domain and the range, right? This set, this transition function maps an element of the domain set into an element of the range set. Okay? So both the domain and the range now for the GNFA are different. So here it is given to you, and later, next session we'll write out the formal definition of a GNFA, and it'll include this. So this is the essential difference between a GNFA and an NFA. Right? So now with the automata we've done so far, the domain was a Cartesian product. So its members were, like on the left side of the pair, the left member of the pair was a state, and the right member of the pair was the input symbol that's currently being read by your automaton. Okay? Well, in the case of a GNFA, you have two states. Right? That's what's different. and but it's still a Cartesian product, a cross product. Right? You're still talking about ordered pairs, and the first member of your pair will be a state. Any state, doesn't matter, except, but not the accept state. So in other words, in this set of states, you could have the start state. And a similar comment here, except the states here, the set of states, do not include the start state, but they do include the accept state. Right? So with those two exceptions, you've just got the set of states and the set of states. And they map, so you've got effectively two states. So that would be like, that might be like your state Qi, and that might be like your state Qj. Okay? And so that's the domain. So it's the Cartesian product of two states, well, sets of states without these two, and the range is it's all it's a rather large set, exaggerating. It's the, well, he calls it collection. I don't know why he does that. He keeps using different words for set. Anyway, class, collection, and others. Anyway, so it's this here now is the set of all possible regular expressions that you can create from your alphabet, the possible input symbols, big capital sigma, and that's what R is. Okay, so you're mapping the state, let's say from Qi to Qj, and the output will be some regular expression. So for example here, if you put into delta Qi and Qj, so Qi and Qj, the output would be R4. And if you put in Qrip and Qj, the output would be R3, like that. Okay? So the delta, the transition function for a GNFA maps two states, like the one you start with. I don't want to start states be different. Well, let's say Qi. It maps Qi to and Qj to it's the label, the regular expression that is the label between those two states. Okay, does that seem sort of reasonable, right? Okay, well so that's the end of that session. It's just looking on. Yeah. Now in the next session, I'll give the formal definition of a GNFA, which will include this delta, of course. And all the rest is pretty much the same. And then we can get back to proving the only if part of the formula, the theorem saying that a DFA and a regular expression are equivalent. They're effectively the same. Okay.